Right, so in this example, we're going to continue working with semantic segmentation, but we're going to switch gears now to a multi-class problem. So instead of having like a yes, no, presence, absence, true, false type prediction, we're going to have multiple categories. So for example, in our first semantic segmentation example, we looked at extracting mining from topo maps. So we basically had two classes, mining or not mining. And then in our second example, we used the NRIA data set and tried to differentiate buildings and background, or buildings and not buildings. So in this example, we're going to look at differentiating four categories, and we're going to make use of this data set. So this is the LandCover.ai Dataset, which you can get from this site. There's two versions currently, and I actually built this using version 0 because that's what I had whenever I started doing it, but there's a new version now that's added a class, so buildings, woodland, water, and road, and the original was building, woodland, and water, and then really there's a background class in both. So basically this is four categories or five. So we're looking at these four, we don't have the roads differentiated. Okay, and then if we, and then just if you're curious, if you go, this data was presented in this paper, so LandCover.ai Dataset for automatic mapping of buildings, woodland, water, and roads from aerial imagery, and you can read about the data there. Just a couple specifics about this data set. These are different aerial orthophotography tiles for different areas in Poland. You can see the distribution there in Poland. And you can see there's a lot of variability in the data in terms of like the tone and texture and whatnot. So the goal here was a pretty heterogeneous set of image tiles to experiment with, things like transferability and generalization and whatnot. You can see the experiments that they set up here and the accuracies that they obtained, so on and so forth. Okay, so if you want to download this data, you can do so from this site. So there's just simply download here, there, and then you'll get a folder that you're going to have to uncompress. So let me show you what that looks like on my machine before we get into the code here. Okay, so just go into this folder here, LandCover, and then okay, so the data that I downloaded was in. Well, it just downloads into this folder here, and you can see that basically you get a set of images. These are the images here. And then you also get the associated masks. These don't really show up as anything. Basically, it's a 0, 1, 2, 4 mask. 0, 1, 2, 3 mask for the three categories, and then 0 is background. And then the rest of these were things that I generated. A couple other files that download with the data is this split.py file, which is a Python script, and then we have the training, the train and val, and I believe there's a test text files. So what this split file does, let me just open this up in a plain text editor. So if you open this up here, you can see this is a short Python script that goes through and generates chips from the larger tiles, which we will look at, which we'll use a modified version of. And then once you make those chips, it generates a series of chips that have already been broken up into test, validation, and training, and we're going to use these files to specify the data splits. Alright, so let's go ahead and move in and start playing around with this data set in our code. Okay, so we're going to switch over here to RStudio. So again, the first thing we want to do is make sure we have Python ready to go. So again, I already have an established Python environment I set up with Anaconda that has all the tools that you need to do deep learning with PyTorch, plus some other like geospatial packages like Rasterio, and then just your general data science packages like Pandas and NumPy and whatnot. Okay, so we load in reticulate, we change to this Python environment, and then we check our configuration to make sure it looks like what we'd expect. Okay, so you can see there it switched over to the Python environment. Alright, so our first step is to split up to build out the image chips. And in the first two examples with the topo maps and the NRIA data set, we did that using an R script that we built and then we configured for these different tasks. Instead of doing it that way, in this example, we're going to use the script, the Python script that the originators provided, but with some minor edits. Okay, so here we go. So this is that script. So note these are some imports: glob, OS, CV2, which computer vision. Then I specify some directories. I'm going to save the images to this directory. I'm sorry, the images are stored in this directory, the tiles, and then the associated mask are stored in this directory. And these are going to be our new directories to store the image chips and the associated mask chips. We're going to shoot for a target size of 512, so 512 by 512. And then here we're setting up our image paths. So it'll basically be the image directory, and then I'm sorry, what this is doing is it's listing out all the files, right? So this is listing out all the image files in our image directory, and then all the mask files in the mask directory. And here we're just sorting them alphabetically, so to make sure that the images and the masks line up, or they have the image and the mask have the same index. And then we set up a for loop here that goes through and does the split. So for each image, it's basically going to pull in the image and mask, and it's going to read those in using the CV2, so OpenCV. And then if it has a mask, then it basically is going to go through this process, and this is their looping that goes through and creates the tiles. A couple of changes that I made was I changed. The original script writes the images out to JPEG and the mask out to PNG. I just had to write everything out to PNG. Also, the masks were prefixed with an _M, but since they were in different folders, I just used the exact same name. So the image folder and the image chip and the mask chip will have the exact same name. They'll just be in different files. And here you can see we're using CV2 again, or OpenCV, to write those files out, and then it's going to print a processing message at the end of each iteration there. Okay, so anyway, we basically just used the script that the providers created, but we just swapped out our own directories, and I made some slight changes, like changing the path here, and then changing the extension, and then dropping the _M there. Okay, so when I ran that, what I end up with is, let's see here, we have our mask folder here. Oh, sorry, that's not it. Our chips folder. And in there we have an image folder, and that's going to have all the image chips. So you can see we ended up with 10,674 image chips. And then we have the associated masks in the mask folder. Okay, so let's just have a look at this data before we move on and actually do any work with it. So I'm just open up QGIS just to visualize the data in a GIS. All right, there we go. All right, so let's open this up, and then I'm just going to go into that directory. And we want to go into our LandCover directory. And first off, let's just pull in one of the images. So let's grab one here. Well, let's grab the first one. So that's our first image. And then the associated mask, which would be masks here, draws over top of it. You can see there are codes there. Let me see if we can change the symbology so we can see each code. And we'll change this to, let's see, paletted unique values. And then add. Those are our 3 values. There we go. All right, so as you can see here, we've got forest, water, background, building, and there's not much of that here. And then obviously woodland. Okay, cool. So that's just some work with the data. Okay, so now we're ready to go in here and actually prep our chips. So we're moving into this prep chip list script. So again, I'm just pulling in some libraries here: dplyr for data manipulation, stringer for string manipulation, Terra for working with geospatial raster data, and imagr for working with image data. Let's run that. Okay, and then again, they already the originators have already split the chips using. So I'm just reading in those text files. So the test, train, and val files. Again, these are shipping with the data. These are not something I created. So you can see the data partitions. The training chips, there were 7,470, and then you can see the split there of test and validation. Okay, and then I'm just renaming the column here to name. Okay, and then I go through and turn this into a data frame that actually has the paths. So if we go into one of these, basically it's just a name. It doesn't have the file extension or the path. So what I'm doing here is I'm just adding in the path for the image and the mask, and then adding the file extension on the end. So if we run all these lines of code, now if we go in here, we now have the name and then the image path, the full path with the file extension, and then the same thing for the mask. Okay, and then I just write that out to a CSV file, and that's it. So that was all I was doing here, was just some simple, I'm not running that because I already had these, but I'm just doing some simple prep of the data. So similar to what we did with the other data set. So we have a data frame where we have a full path for the image, for each image and each mask, and then we have our separate data sets. Okay, and then after that, we're actually ready to go in and start training our model. So what I'm going to do here is mainly focus on where there are differences from what we had done before, to try to adapt our scripts to work better, or to work with a multi-band classification. So here I'm just importing some packages. Nothing really new there. Again, we're still relying on our segmentation models. Again, whenever you import these packages, if you get any error messages or can't find a package, then that indicates that either one, it didn't set the environment correctly, or something's up with your environment. So you can see this is happening already here. I've got a DLL load failed error. So let's let this finish, and then we'll have a look at what's causing that. I'm actually not sure what causes this, but I run this a lot in R. And generally what will fix it is to just restart the R session and then change the Python environment again. So I'm going to do that. So I'm going to go to session, restart R. Now I need to go back to my prep Python here and rerun all this to get my environment loaded in. And that looks correct. And then we'll go back to our train here, and we will run all our imports. Hopefully it should work now. Okay, looks like we're good now. Again, I'm not really sure what causes that, but again, restarting the R session generally fixes it. So anyway, that we should be ready to roll now. Okay, so now that we got our packages loaded in here, I'm just changing the working directory. This is where it's going to end up saving our models. Then I'm reading in our train and chip lists, and these are the ones that I created with my script, where I added in the file extension and then the full path. Okay, so I'm just doing train tests now because we're just building out to train the model. Okay, now I'm setting the mode for semantic segmentation models to multiclass mode, and then we're setting it to multiclass, right? So that way it knows it's multiclass. We're going to again use our ResNet 18. Again, there's better or more complex backbones. I'm just generally using something small here because I don't want it to take forever, since this is just an example. And then we're going to start off with the image weights. I think that makes sense here because we basically have RGB images, which is what the ImageNet images are. And now, instead of just having one class, for example, mining or building, we have our background, our building, our woodland, and our water class. It's important that you put these in the right order. So this is the order in which they're indexed. So 0 is background, 1 is building, 2 is woodland, and 3 is water. If you get them out of order, then the indexes and the class strings or actual names are not going to line up. One thing that's kind of confusing with multi-class classification is that you can't use, let's see here, sigmoid activation for the last component, because that only works for 2 classes. So then your option is either to do a softmax or none. So what I'm doing here is none, and then we'll actually apply the softmax after we get predictions. So we're just going to have a return back the raw logits as opposed to a probability. And then CUDA again so that we are using our GPU. All right, so let's run that. That's just setting some values. Again, this is same as we had before. I'm just checking to make sure it sees my GPU. So it looks like that's good there. Okay, so the next step here is to, again, build out a data loader for this specific problem. So I'm creating I'm subclassing the tensor dataset class. I'm calling a Multiclass Seg Dataset. And then again, you have to have the 3 components. So the init method there, the get item method, and then lastly the length method. Okay, so again, in the init method here, we're just having it effectively grab data from a data frame. So the inputs here are self, data frame, specify classes, specify transforms. So here, again, just pulling in the data frame, class is equal to class, transform is equal to transform. And then the get item, again, is how it's going to generate a image chip pair for each, like tensors of from image chip pairs, right? Okay, so basically in this example, the image is in the second index position, and then the mask is in the third index position. You might say, well, wasn't it 0, 1, 2? So shouldn't it just be 1 and 2? Well, whenever I call this in, let me show you that real quick. Just look at the validation chips here. It adds this other field. So again, our image is at index 2 and our mask is at index 3. So 0, 1, 2, 3. All right, so there we're effectively telling it where, so there we're grabbing the image name, there we're grabbing the mask name, then we're reading in the image using IMRead from the CV2 there, open computer vision, and then we're doing a flip of the color channels, blue, green, red to red, green, blue, and we're reading in the mask unchanged. Then we're changing the image to an unsigned 8-bit type. And then lastly, for the mask, we make sure we just have the first, just a single band. So all the rows and columns, the first, and then the first band. And that's just in case I had an issue where it was like adding extra bands. So that's just to make sure we only have our band that we need. Okay, and then if we apply transforms, then we will apply the transforms to the image and mask, and then we'll pull those out as separate objects. So up to this point that we're working as NumPy arrays. Now we'd like to convert to torch tensors. So that's what this from NumPy function does. So we're converting the image to a torch tensor, converting the mask to a torch tensor. And then remember that the band order expects channels height width as opposed to height width channels. So we're using this permute method here. So channels height width to change the order. And then this is 0 to 255, so we convert the image into a 0 to 1 scale by dividing by 255 and converting it to float. And then the mask here, we're converting to long, and we're unsqueezing to add another dimension, and this is because we're going to end up with a height width array, so with 2 dimensions, but we want to add on a channel dimension. Again, that's common when you have grayscale images. It's kind of confusing because you either have channel height width with just one channel or height width with no channel, and it's effectively still the same array. But it's expecting here it wants to have that first channel or dimension. Okay, and then the same thing if you don't have transforms, we're just skipping the transform part, and then it'll return back the image and mask pair. And then lastly, we have the length function to return the length of the data frame. Okay, so that should yield back a data load or a data set class there for this specific problem. Okay, and then again, we're using the argumentations library to apply some transformations. random brightness contrast changes, horizontal flips, vertical flips, median blurs. So again, we've looked at this in some of the other examples here, so there's really nothing new there. So again, we're just setting those up. Okay, and then now we can define our training data set and our test data set. So we're just feeding in our data frame, specifying the classes and the transforms we want to use, and then print that to see what we end up with. So we have 7,470 training samples and 1,602 testing samples, which is what we expected based on when we created our chip lists. And then the data loader, the main thing here is I'm on a Windows machine, so I'm setting the number of workers to 0, and the batch size I'm setting here to 8. Note that these are bigger chips than what we used in our prior example. So we have 512 by 512 as opposed to 256 by 256. So each chip is effectively 4 times as large, right? So for that reason, I decreased the batch size to 8. Again, if you have any issues, you may need to drop this even further. I've seen people do, when they have chips of that size, as low as like a batch size of 2. But 8 seemed to work for me, so again, you may have to fiddle with that if you run out of memory. So there's our data loaders. And then again, we just pull a batch to look at the dimensions to make sure it makes sense. Okay, so our images are dimensions 8, 3, 512, 512. So 8 again is the batch size, 3 is the number of channels, 512 by 512 is height and width. For the mask, it's the same thing, except the channels is 1 as opposed to 3. And we can see the first one is float 32, so that's the 0 to 1 for the image. And then our mask is int 64 or long, so it's a long integer because we only have 0, 1, 2, and 4 values. Could even be a short integer, but we're just using a long integer there. Okay, and then just looking at one image here. So again, once we pull one image, we lose our batch channel, and we should have a range that makes sense. So between 0 and 1, and then for the mass 0 to 2. So there must have not been any water in that example, right? Because that would have been index 3. And then I'm just plotting one of the images and its associated mask. Yeah, so that's basically a forest. So that would be at index, should be index 2, and then background is 0. So it looks like there's only 0 and 2 index in this one. And again, you'd probably get a different one since there's randomness there. Okay, so now we're ready to initiate a model. In this example, I'm using UNet++ as opposed to UNet or some other semantic segmentation method. You remember in the TopoMap example, we worked with UNet, and then we switched to DeepLab v3 Plus for the arena building data set example. And just for another, use a different algorithm in this example, we're switching to UNet++ as opposed to UNet. Okay, so again, here we're just initiating it. Note here, we're specifying it's 3-band image. We're using the ImageNet weights, the ResNet 18 encoder. There's 4 classifications, and our activation function is our activation function. Excuse me, which in this case is none, right? We're not using an activation function to get back to raw logits. Okay, so there we've initiated our model. Okay, so next step is to set up our loss. So in this example, we have a multi-class problem. So what I used was dice loss. I decided to use this as opposed to like cross entropy loss because of data imbalance issues. And I had to set the mode to multi-class. That's really important. If you leave it as like single class or binary or whatever, then it's not going to work correctly. So you definitely want to change this mode here. Note that I had issues with this when I installed the semantic segmentation model using pip. I'm not really sure why. So if I installed it directly from the GitHub repo for segmentation models, it worked. So I'm not sure the reason for that, but I had to install it from GitHub to have these multi-class loss metrics work. I also ran into an error where it would say there was no name associated with the dice loss. So that's what this is doing. It's just creating that name object there, which it'll need later. I'm not going to have it report any metrics via during the learning process. So it's really just going to print out the dice loss for the training and then the testing or sets. Okay. And then we're going to use our Atom Optimizer. Note here I set a learning rate this time. That's something you could experiment with to see if it has any impact. Then we define our training and our validation epochs. Okay, and then lastly, we're ready to actually train the model. Here I just did a really simple model. I'm just running it for 10 epochs. It's going to log the training loss, the test loss, and it's going to save the model. So it's not going to really test to see if the model improved or not. It's just always going to override it. So whatever we get, we're going to get the model, no matter what model it gives us the best loss, it's going to just give it back the last one, which isn't optimal, but I just wanted to do something simple here. So we're going to train this model for 10 epochs. At the end of each epoch, the saved model is going to be overwritten, so we're going to get the last one, so the model at 10. Again, I'm not going to run this here because this takes a while, but when I ran this before, it took a couple hours, maybe longer, it could be longer or shorter depending on your infrastructure. If you switch to a different backbone, change the chip size, or change the learning process or whatever. So, that's going to be computer specific. Okay, so now I'm going to load in my saved model. So this is now this best model object. So that's all the weights that were learned. And then I want to go through and actually see how this does predicting onto some new chips. So now we're pulling the validation chips as opposed to the test or training chips. Again, I'm just running that through the same dataset subclass, and I'm using my test transforms, create a data loader for that object, define a validation epoch using that new data set, and then here I can just run it and get back some stats. So let's let this run just so you can see what happens here. Okay, there it goes. So it's going through, and it's, here we're updating the loss, right? So again, dice, if you're familiar, is effectively kind of like harmonic mean of precision and recall, and since this is multi-class, it's averaged across classes. It's like kind of in like the 85% accuracy range now, just overall. And then lastly here, we just have a script that goes through and makes a prediction on a subset and then prints those out so we can see them. So whenever this is done running, we'll take a look at that and just to see what it looks like visually. I generally think, generally speaking, when you're doing this type of work, it's good to get some type of quantitative assessment like we're doing now. And it's also a good idea to get a more qualitative visual assessment. So in short, it's good to visualize the results and not just to rely on your accuracy metrics or error metrics. All right, so done. All right, so 0.16. So that seems reasonable. All right, so let's have a look at some of our output here. So again, we're defining a visualization function, and then we're going to plot that out. Note that I had to do some changes from how I was doing this visualization before, since now we're switching to multi-band. Okay, so a couple key points here is that remember what we were getting back from the model for each pixel was the raw logits for each class. So I'd like to convert those to probabilities. So here I'm basically pushing an image to the device, adding a batch band, predicting on that image, and then once I have that data, I run it through softmax to go from the raw logits into probabilities, and we're doing that along dimension 1, and that's because the first dimension is the batch, the second dimension is the channels, which in this case are the logits for each class. Okay, and then, sorry, this is actually define the softmax, and then this applies it to the data. And then to actually get back, instead of the probability for each class, I want the index for the class with the highest probability. Then I run this argmax. So effectively what this does is it's going to return the index for basically the channel number that had the highest probability in this dimension, which is dimension 1, which is the channel dimension. So the first channel is the probability for class 0 or background. So that 0, 1 is, what was it, building, 2 is woodland, and 3 is water. So we have 4 probabilities, and it's just going to give back the index for the highest probability. And then, getting rid of our batch dimension there. And then we, and then we send that back to the CPU so that we can turn it into a NumPy array, and then visualize it. Okay, so let's run this and see what some of our predictions look like. Okay, so you see over here the predictions have drawn. Sorry, I actually think, let me run this again with the window bigger just so we can see it better. Oh, it's just telling me I have a lot of windows open there. Okay, so this just looks at some of these outputs. This green is forest, and I believe that's the water, and then the background. And so this is the prediction, and this is the hand-drawn, just for comparison. So right now, as you see, it's not looking too bad. It's not great. There definitely are some issues, but we're at least getting something that seems reasonable, something you would expect, not some nonsense. Okay, and then the last two components of this is similar to what we did before, but with just a couple changes. So we're going to switch now to our infer Python function. So now we have a model, we can use it to infer something. All right, so again, in this one, we're just we're importing in our libraries, changing the directory. We actually don't need to do that. I was just pulling over some code there. So let's just run down to the model. Basically, I'm just getting a model back and then reading in my learned weights into it so I can apply it. Okay, and then we define our infer function. Note that I had to make some changes here in comparison to what we were doing with the single class examples. The main difference here was that once we do the prediction down here, we have to do what we did in the visualization function, right? So run our prediction, apply the softmax to go from logics to probabilities, apply that to the predictions, and then take the index of the highest probability to get the hard classification. And then other than that, this function is effectively the same or very similar to what we had done with the binary methods. And then we write that out. Note that I had some issues with the original data, and I'm not really sure why, but it kept giving me an error. So I actually had to go into my GIS software and save a copy of the images out to get them to work. I'm not really 100% sure why that was the case, but it seemed like the raw input images were not playing well with rastereo or one of its dependencies. So you may or may not run into the same issue if you're fiddling around with this data. And again, my workaround was just I made a copy of it. I just exported it from my GIS software. Okay, so I have this test image, which is just one of the images that I made a copy of. And this will be the prediction. So I'm just going to push that. I'm just going to put 2 on the end because I already ran this. And then we're going to do, this is our chip size. We're going to overlap by half in both directions, crop off 70 cells, and again, it's expecting a 3-band image. Okay, so let's hit that. Okay, so the way this function is written, I believe I mentioned this before, is it's going to push this calculation out to the GPU. So it's going to run everything on the GPU, which means it should actually run pretty quick. So we should get an output in a reasonable amount of time. Okay, and then it kicked back, so it looks like it made that prediction on that entire tile. Okay, so let's go into our GIS here and open up that prediction. So we want to go to our image, which I believe is this one. And let's just do a zoom to, let's see, zoom to layer. Okay, so here's an image. And then let's pull in the mask. So we're going to go to it. I wrote it into this predictions folder, and this is our new one, test 2 there. So there's our prediction. Let's go in and change our symbology, and we'll do an apply. Okay. All right. So again, background is our like cyan, light blue. It's a weird color for that. And then our green is forest, and then blue is water, and then the red are the buildings. So if we zoom in here, just so we can kind of see how that looks. It's actually not too bad. This, however, I just randomly grabbed an image to test this on, so this may have been one of the training samples, which means this may not be representative of how it would do on a raw image. I just, again, grabbed one kind of randomly. So, doesn't look terrible, but definitely some room for improvement. Again, I only trained this for 10 minutes. I didn't unfreeze weights. So there's things you could do to potentially improve it. All right, so lastly, we may want to, again, do an eval on this using the full tiles as opposed to individual image chips. So again, we'll go to our eval script, which is similar to what we had done with our last set of classifications. Again, I had to make some changes in here since this was multi-class. I had some issues with the positive case fields because in this case, since it's multi-class, it really doesn't make a lot of sense. So anyway, I had to do some editing to this relative to how we had used it for our binary classification, mainly just removing any of the positive case calls in here. But other than that, it's effectively the same. So again, we're going to create this eval function, again working in R as opposed to Python, and then we can call it. So again, I'm just grabbing the mask associated with that test image, and then my result, which I guess is 2 this time, but it's basically the same, and they're providing everything as raster data. Background 0, these are our codes, so I think everything should work. And if we run this now, we should get back our this might take a minute, but this will spit back the accuracy assessment metrics for just this single image. Okay, so that's done. So let's call our object here so we can see our eval results. I'm going to do eval out and just have a look here. Okay, so here's our error matrix. So the columns are the reference data, the rows are the predictions. Again, our diagonal represents the corrects, and then off diagonals are errors. And these numbers are fairly large, and that's because we're dealing with single image or single pixels, and there's actually a lot of pixels in this image because the cell size is pretty small. Okay, so the reported overall accuracy comparing that mask we got to the hand-drawn mask was 96.7%, which is pretty good. However, you can see kappa is kind of low, comparatively speaking. So there's some error here, but it seems that overall it's doing pretty well. Again, if we look at users and producers accuracy here, we're seeing background's pretty high, 99 and 97. Building is kind of moderate, 78, 79. Water, it seems like the major issues here are issues of water and woodlands for the user's accuracy. So our producers' accuracies generally are not that bad. They're all like, so round this up, roughly 80% or above. It seems like though we have some issues with users accuracy for the water and woodlands class. So maybe one thing we could do is prioritize that with like class weights or something. Yeah, and then we have our allocation quantity disagreement component. So again, there's lots of information that gets spit out there. Something else you could do, obviously, with this is you could run it in a loop and get a bunch of results for multiple tiles, and then average those out. I guess something we did when we looked at like the topo maps, for example. Okay, so this is our first multi-class example. and extending upon what we did with our two single class or binary classification problems.